All right, so we've done chaining as one of our collision strategies, okay? And remember, collisions just mean two things are hashing to the same index, okay? Now, we're going to have a few more strategies that are kind of interesting, and we'll talk about them, and that's where we'll end hashing, okay? One of them is called linear probing. Okay, so first things first, actually, let's talk about the scheme of modulo 10, because it's important. Okay, so modulo 10, if you haven't kind of 2, 3, 4, 5, 6, 7, 8, 9. Okay. Modulo 10, and convince yourself of this, will always give us, if we modulo 10 of any number, it'll always give us a value between 0 and 9. Okay, and why is that the case? Well, you can imagine 10 modulo 10 is going to be a remainder of 0, right? And then 11 modulo 10 is going to be a remainder of 1, right? 10 goes into 11 one time, right, with a remainder of 1. And then 12 modulo 10 is going to be 2, and 13 modulo 10 is going to be 3, and 14 modulo 10 is going to be 4. All the way up to 19 modulo 10, which is going to be 9, all right? And then 20 modulo 10, well, that's 10 goes into 22 times with a remainder of 0, and we're back to 0. Okay, so what modulo 10 does is it ensures that we're always going to get values between 0 and 9, which means we could have a limited space in our hashing array, and we can still store all the values. Okay, especially in chaining. In the chaining scheme, that works out nicely. Okay, and so that's the power of modulo 10. If I have a hash table of n things, okay, what I'm going to do is I could come up with a simple hashing scheme of modulo n. And that's the simplest hashing scheme that you can kind of think of. And a very common one, too, okay? It's not necessarily the best, right? But better hashing schemes or better hashing functions are a whole string of mathematics that we're not going to go into. We're just going to talk about the general concepts of hashing. All right, so we've talked about chaining as one way to deal with these collisions, right? Clearly, we're going to have collisions if we take the name of the person, right? Sandy Newman. And Elise. What was Elise's last name? Katmer? I know this wasn't Elise's last name. Oh, I feel so bad. Elise Katmer. Okay, and let's say we also have Ronau Themers. Okay, so Ronau Themers is 12. This is 11. This is 11. And we have Terry, 2, 3, 4, 5. What do we want? We want 11. And we'll do Satmer. 1, 2, 3, 4, 5, 6, 11. Okay, so this is 11. Okay. All right, so the scheme, another scheme we can come up with is called linear probing. And what does linear probing do? Well, what we do is we insert, let's actually just insert these two. Okay, so we insert these two. Okay, well, Sandy Newman, God damn it. It's all right. Sandy Newman is 11, right? 11 modulo 10 is 1, so we'll put Sandy Newman here. Okay. And Elise Katmer, well, that's a length of 11, right? 11 letters. 11 modulo 10 is going to be 1. Uh-oh, Sandy Newman's there. We could chain it if we were doing chaining, right? We could make it into a linked list. But if we're not doing chaining, another thing we might do is we might just say, oh, what we'll do is we'll just put it to the right there, okay? So now we have Elise Cadmer here, okay? And then, so don't worry about these right now, okay? Just say these two. And then if we want to look up Sandy Newman, well, we look up Sandy Newman and we find Sandy Newman at the index we think Sandy Newman's going to be at. That's fine and good, and we grab, you know, whatever we want. The number of credits Sandy Newman currently has or something, right, and return that. Let's say we wanted to do a credit check on Elise Cadmer. So we take the name, we have 11, we modulo it by 10, it's 1. We come over here, okay, Sandy Newman's there. And so what linear probing does is says, wait, but we're not done because we still have to look to the right to see if Elise Cuthbert or Elise Cadmer. Oh, Alicia Cuthbert. That's a person, right? Elise Cadmer is there, right? And we look to the right, and sure enough, Elise Cadmer is there because it could still be to the right of this thing, okay? Let's say we look for Terry Satmer in here. Well, Terry Satmer is 11, okay? And so, Terry, we come in here, and Terry Satmer is not in the place we think it's going to be. So we go to the next one, and Terry Satmer's not there. And we go to the next one, and Terry Satmer's not there. And so we're like, okay, Terry Satmer is not in this. Okay, there's a little asterisk on that we're going to get to in a second. But so far, so good. All right, so we kind of have some sort of scheme. We index to the place. If it's not the one we're looking for, we keep on looking right. And then if we come up to a space that's empty, then we know, hey, that thing is probably not in here, okay? Asterisk. That's not the rule, okay? So now we insert Ronald Themers. You know that classic name, Ronald Themers? Well, here we go. 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, Ronald Themers is 12, all right? And we try to insert Ronald Themers of the Themers clan. How many Themers? It's like Smith, right? Okay, and so we're actually going to hash to 2 here, right? Because 12 modulo 10 is 2. All right, and uh-oh, that's taken. So what do? Well, we do the classic linear probing thing. We just put it over here, okay? So it's a really simple scheme, okay? And all right, and so Ronald Themers, let's say we're looking up Ronald Themers. We come here to 2, it's taken, but that's okay because we keep on linear probing to the right because, and we find Ronald Themers here, okay? And if we look at something else like Terry Satmer, well, Terry Satmer, we're going to come here, not there, not there, not there, but we keep on probing because it's got stuff in it, and we come to an empty one, and we're like, okay, we're done, okay? Let's actually, so we've inserted Ronald Themers. Let's, for fun, insert Terry Satmer, okay? So we insert Terry Satmer now. Okay, we can't insert Terry Satmer there. We can't insert Terry Satmer there. We can't insert Terry Satmer there. So we're going to insert Terry Satmer here. So Ronald Themers and Terry Satmer, 2 people whose parents couldn't think of a name. So we have Terry Satmer over here, okay? And if you think about it, it'll still work, right? We try to look up Terry Satmer. It takes us to 1. We start linear probing to the right. Not Terry Satmer, not Terry Satmer. Terry Satmer, we found it, right? Or we run into a space that's empty. Now, someone comes along and says, okay, Elise Cadmer has graduated, all right? And so what we're going to do is we're going to take Elise Cadmer out of this table, okay? Because this table is only for our current students. That could easily happen. We might have 2 different hashing tables, one for all students and one for current students, just to make the lookup that much quicker, right? And to have less collisions. And so we say, all right, well, at least Catmer 11, we use our hashing function where we modulo by 10, and now we get to 1, and well, that's not at least Catmer, we get to the next one. Oh, that is at least Catmer. Okay, so we take at least Catmer out of our thing. Okay, so now it's an open space. Okay, and now, Terry Satmer graduates, and so Terry Satmer comes in and asks for a credit check. You know, Terry Satmer wants to know when graduation's gonna happen. And so what we do is we take Terry Satmer's name, 11, right, and we modulo it by 10, and we go to 1, and it's not Terry Satmer, and we go to 2, and it's empty, all right, and we don't find Terry Satmer, but Terry Satmer is in here. It's at 4. So there's something weird here. We can't just say we're going to go till it's empty, because if we go till it's empty in this case, we don't hit Terry Satmer. So there's two notions here in probing. There's a notion of empty since beginning, and empty because of a delete. Okay? So empty since beginning and empty because of the delete. And when we delete Elise Catmer from here, what we're going to do is we're going to mark it empty because of a delete. God damn it. What is going on? Okay. Empty because of a delete. Okay. We're going to mark it empty because of a delete. All right. And when it's empty because of a delete, that means keep probing. Okay. If it's empty since the beginning, that means we're done searching. Ah! Oh my god! Okay, that means we're done searching. Okay, so when we're empty because of a delete, that means empty from beginning. That means we're done searching. If we're empty because of a delete, that means keep probing. Okay, so now when we want to look up Terry Satmer, one of the most common names in the United States today, we'll start at 1, right? Because 11 will hash to 1. And then we'll look at 2, it's empty. Okay, well, since it's empty, we say, is it empty since the beginning or empty because of delete? It's empty because of delete. That means we keep probing. Okay, and then we get Ronald Temer, so it's an item, so we keep probing, and then we get to Terry Satmer. Okay, if we have another person who's 11, oh my god, Sinew Samter. And it's 11. Classic Sinew Samter, all right? And we say, is Sinew Samtering here? Okay. One thing we'll do is we'll come here and we'll say, okay, that's not Sinew Samter. That's not Sinew Samter, but it's empty because of delete. That's not Sinew Samter. That's not Sinew Samter. Okay, now we've gotten to a point where it's empty since the beginning, and so we know Sinew Samter is not in here. Okay. All right, so let's say Sinew Samter is a new student, and so we want to insert Sinew Samter. We come up here, Sinew Samter is not there. We come to the next one, and it's empty. Now it's empty because of a delete, but it's still empty. And so we're allowed to insert into an empty because of a delete one. And that is, so empty because of a delete means you keep probing, but it's empty, so you can insert into it, okay? And so that's the idea. One is that if you have a collision, you keep on going to the right. So the rules of linear probing. So insert into first open space and to the right. And you wrap around, okay? You wrap around. And if you run out of space, you need a bigger hash table. There's nothing else you can do here. Chaining, you don't, right? Chaining deals with that in a really, really smart way. But if you run out of space here, you're gonna run into trouble, okay? Okay, so you insert into the first open space, all right? And then if you are looking up a value, so when looking up a value, go until empty since beginning. Okay, and if you hit an empty since beginning, that means the value's not in there, right? Otherwise, if you hit the value before an empty since beginning, that means the value is in there. I haven't written all the rules out here because I'm running out of space and I can't write like that. But so those are the rules, right? So we insert, we go to the place we want to insert into. If that place is taken, we keep on probing to the right until we find an empty space and we insert into there. Okay. Now, if we are looking up a value, right? We go to the space that it should be. And if it's not there, we keep on going to the right until we find that value, okay? But if we hit an empty space because of a delete, we keep on going to the right, all right? If we hit an empty space since the beginning, we know we're done and that value is not in there, okay? So this means keep on probing, and this means you're done, okay? And that's basically it. That's linear probing in a nutshell. So it's another scheme to deal with collisions, right? Oh right, I dropped that stupid cap. And so it's a very simple scheme to deal with collisions, and it avoids having to make a linked list at all of these places, but it has its downsides too, right? You're gonna end up, if a bunch of things are probing to 11, right? Then you're gonna end up doing your search through the array anyways, and it's going to end up being O of n, right? So really, in any of these schemes, you want a function such that things are evenly distributed throughout this array, which is the challenge in hashing is finding that function.